All right, let's look at Newton's universal law of gravitation. Isaac Newton found and described the force between two objects of mass. This is a field force, as we've already mentioned, that it doesn't require contact, that, for example, the planets experience gravitational forces between them and one another, between them and the sun. We experience a gravitational force between us and the Earth, but we also experience gravitational forces that are small but measurable for sure between bodies like us. Like, so you and another person, there is this force that pulls the two of you together. It's almost like a romantic movie. They should make a romantic movie called Universal Gravitation or something like that, maybe. And this is actually measurable, and they've done this in a lab where you can actually measure these forces. Isaac Newton showed that these forces, which I've labeled here as F12 and F21, that they are between two bodies of mass, and they can be characterized, the magnitude of them, for example, F12, the magnitude of that force is equal to the mass of one mass, the mass of the second mass, divided by the distance between them squared, and then there is a gravitational constant, G. Let's see, G is 6.67 times 10 to the, gosh, I think it's minus 12. Let me just double check. I can never remember these things. No, 10 to the minus 11. 10 to the minus 11. And that is in meters cubed per kilogram second squared. You'll be given that constant. It's just a physical constant that describes the relationship between this force and the masses and the distance between them. All right. One thing to note about this is that this force is dependent upon both masses, so the force is equal in magnitude, and this will come up with Newton's third law when we get to that. So F12, the magnitude of that force is equal to the magnitude of F21. So if I'm standing on top of the Earth, here's me, there's the Earth, here's me. I'm standing on top of the Earth, and the Earth is pulling down on me with 700 newtons of force. Well, in a similar way, I'm pulling up on the Earth with 700 newtons of force. So literally, we're all walking around pulling up on the planet Earth, which is kind of a cool idea to think about. All right. Now, in Newtonian physics, all forces are instantaneous. However, all the forces that we see now require some means of transferring them. Primarily, these are contact forces, and the means of transferring them are through touch in some way. How then are these field forces transferred? And that's not fully known, neither for gravitational or electronic forces. And do they require some time to transfer? So from the first to the second mass, that is, does it require some amount of time for this force to come into play? If we could just imagine that this mass just instantaneously appeared, what would be the amount of time for the F21 to actually come into play? Now we know that contact forces, they appear at the point of contact. But what about these field forces? Einstein said that if you could remove the sun in an instant, just completely remove it, make it vanish, and that mass would disappear, then the planets would not react immediately. Right? They would lose that gravitational force, but not immediately. And he predicted the existence of gravity waves. These are also sometimes called gravitons. And these are theoretical wave particles that transfer the force of gravity. So it's thought that between these particles of mass that you have these waves or these particles that travel back and forth. They're kind of like photons maybe, photons of light, and they transfer this force of gravity. All right. It's a big deal right now, the past 30, 40 years. Let's see, I will try to find a clip about gravitons. I have one, but I can't post it on YouTube because it's copyrighted. I will place it right here if I find it. Now, there is a big effort to try to detect some of these gravitational waves or these gravitons, and that's called the Large Interferometric Gravitational Observatory, and it's hoping to be the first to detect these gravitons. This is actually in Louisiana. There is actually one in Louisiana and one in Hanover, Washington. The one in Louisiana is up north of Baton Rouge. It's in Livingston, I think. I don't know if that's the town or the parish. I haven't been there. But LIGO consists of these huge blocks of concrete, many, many tons of concrete that will theoretically move when gravitons from cosmic events such as supernovae reach the Earth. So for example, let's say that I have a star over here out in some other galaxy or in our galaxy, and it explodes. It blows up in its final big hoorah. The idea is that it is going to emit a lot of gravitons because it's a very massive event, lots of mass involved, and it's going to emit a lot of gravitons. Now here we are over on the planet Earth, and we have this big block of concrete in Livingston, Louisiana, and it's thought that when these gravitons enter that block of concrete, it will shift slightly. And they use that to predict the existence or to observe these gravitons. Now, they haven't detected any as of yet, but when they do, that's Nobel Prize, my friend. So if you can get in on that effort, or maybe you can come up with a way to detect these gravitons, then please do so. Now, interesting thing about LIGO is it's very sensitive. It's like a very sensitive seismograph. It works in a different concept, but it's very sensitive seismograph. So it can detect very small vibrations. So even though it's pretty far from the coast, it can actually detect like waves lapping on the Gulf Coast. So you say, well, how does it know if these events are just, you know, geological or man-made, or if they're actually cosmic events that are producing these vibrations, if these vibrations are even due to gravitons? Well, that's why they have actually two blocks of concrete, one there and one there. And if they both detect the same event, then they would say with some certainty that they are cosmic and not geological. All right. We'll stop there.